The first step was the decision that this nation's first venture into manned space flight should be a peaceful civilian effort. This was a big first step. From then, the next step was to determine which group would handle it. NASA was chosen as that group. Then plans were made, remade, gone over, studied to decide just what the program should be. It was decided that the program should be the simplest possible undertaking to make an absolute minimum of new developments in order to achieve the program as rapidly as was reasonable and with the highest reliability that was possible. The next step, which occurred very shortly thereafter in the fall of 1958, was the preparation of plans and specifications for the capsule, the calling together of some 40 major aircraft and electronics manufacturers, briefing them on the project to tell them what it was we hoped to buy and issue them a set of specifications so that they could enter into a competition to see who would be chosen to actually produce the capsule. And the next step, that of the detailed design of the capsule and its contents, was undertaken.
Well, actually, it's kind of difficult to describe. I think one of the easiest ways is to talk about a child's top. Normally the top spins on its point. In the case of the Mercury capsule, you invert the top so that the blunt face is down. The point is modified so that it has a rather enlarged neck rather than the point on the end. Or it might be described something like the shape of the television tube that's in the television set. It measures about 6.5 feet across the base, or about 2 meters. It's about 10 feet tall, or about 3 meters from its curved face up to its narrow neck.
The Redstone booster had already achieved a significant record of reliability flight and a launching history which extends over the past 7 years. Of over 40 Redstone launches, only 2 boosters have failed. However, the Mercury spacecraft escape system, which has been incorporated into the Mercury design, would have prevented the astronaut from being harmed in such a malfunction. Changes in the system for the Mercury mission include the elongation of the tank section to increase fuel capacity. This is similar to the Jupiter-C design of the Redstone booster, which was used to launch the first Explorer satellite. Also included in the design change was a new instrument compartment and adapter section to accommodate the Mercury spacecraft. There have been changes in the engine and control system in the interest of simplicity. Also, improved reliability and increased performance have been maintained throughout this program. The development of a mission abort sensing system to assure safety of the spacecraft and astronaut on later launchings has been included. The Mercury Redstone is approximately 83 feet in height, including the spacecraft assembly. This is compared to the standard length of 69 feet on the tactical Redstone. The body of the rocket is approximately 70 inches in diameter. The liftoff weight is 66,000 pounds. This includes the 1-ton Mercury spacecraft. This program was conducted by the Marshall Center and the Chrysler Corporation. Reliability tests were conducted on individual components, subsystems, and systems. Test conditions included excessive vibrations and extreme temperatures. Engineers of the Chrysler Corporation designed and operated a special rock and roll test device which subjected the entire instrument compartment of the Mercury Redstone rocket to environmental stress. This latter phase was devoted primarily to checking out the abort system to assure that it would operate properly on demand and could not be activated accidentally. At the Marshall Space Flight Center, personnel ran structural tests on a new Redstone Mercury configuration, which assured the structural integrity of the vehicle. Units of the rocket were submitted to considerable higher stresses and strains than would be normally encountered in flight. In addition to the acceptance firing of the engines, the Marshall Center is static firing each completed booster of the Mercury series prior to the shipment to the launch site. During these static firings, a detailed measuring program gives assurance of proper performance of the engine. The center also captive fired a complete Mercury Redstone configuration, including a research model of this spacecraft previously flown during a Little Joe test firing.
The pressure suit consists of a hard white helmet with a visor, transparent one, rather reminiscent of a medieval knight in some ways, and a rubber suit which doesn't look at all rubbery. It's quite light and flexible and has a silvery outer coating. And this is to help keep the man cool during re-entry heating. And inside as well, we'll circulate air through it to keep him cool, not only during re-entry, but just to keep him comfortable. There are various straps on it to tie him down securely to the capsule when he goes getting launched and during re-entry, so that he doesn't bounce around any when he finally lands. And there are going to be on it some fittings so that he can have a flashlight, a notepad on his knee, and some other tools that he might need during the flight. Presumably he'll have a place to keep a pencil or some such thing on it. There will be some hoses that go to and from the suit to take air to and from it. In addition, in the event that the cabin loses its pressure, there are some lines carrying air or oxygen to the suit which blow it up. In other words, the faceplate is closed and there's no way for air to get out of the suit. And this increases the pressure within the suit by inflating a second little garment so that the man feels a normal pressure around him, the same as he would here on Earth. This keeps him from boiling or exploding, as he might if he were exposed with no clothes on at all to the complete vacuum of space. The man in our cabin will be keeping cool in part by evaporating moisture through his skin. And during the course of a 4.5 hour flight, this might make him rather thirsty, so that we're planning for our normal mission to have him do a certain amount of drinking. And we would use plain water, or indeed we might use things like lemonade, which would give him some sugar and other things. It might be a little more tasty. In addition, we may, just for a break and perhaps to compensate him for not having his cigarettes along, let him have some form of candy or other food. At the same time, we are seriously considering, although we are still in the development stage here, we're seriously considering using some sample foods that might be of interest in later space flight for him to take in during the shorter flights to see, by use of various tricks such as tracer techniques to see if he indeed absorbs food while weightless in essentially the same way that he does on Earth. We have quite an extensive research program underway looking into what would be the best thing.